All right, we're going to spend a few minutes here talking about earthquakes. You will notice this slide and the several slides that we're going to go through here together are part of a bigger slideshow that I've kind of included in your lab um, materials folder for the week. It is, we're not going to do the entire slideshow by any stretch. Really, it covers a lot of stuff that is more for your lecture exams and your lecture content. So I'm focusing on this within this only in the earthquakes area, and we're going to specifically look at how to use some simple tricks and techniques to find the earthquake epicenter once that happens. So as far as the rest of the notes go, you can just kind of use them as a study tool or companion with your lecture materials, and just focus on these slides for the lab portion. And you will need to know a few of these things within here. So generally, just so you know, earthquakes are simply energy moving through the Earth's crust, or the rock and the dirt and everything. And that is all due to potential stored energy, where giant, huge slabs of rock and crust are kind of being scraped along each other very, very slowly, and pressure builds and they snap eventually. And that causes what we know of as an earthquake. And the actual snapping of that rock happens at a place along a fault, which we call the focus. And you can see that in the little picture down below. If you trace from wherever that snap happens on that focus point up to the surface on the ground where we live, then that is called the epicenter. And earthquakes release this energy in a couple of different kinds of waves, the first being the P waves. And they are quick. They move very fast. As soon as the earthquake happens, they move out quickly, and locations around will feel these waves first because they travel faster than the other kinds of waves. And it's a pulse kind of wave, which in physics you call a longitudinal wave. Basically, think of it as if you look at the picture down below here, think of that as a spring or a big long slinky, and these little areas of compression move through the slinky, or in this case, the rock of the land. And that is almost hard to believe that you can actually have this happen, but the rock gets compressed as the energy moves through. And they move quickly, and they cause a lot of vibration when they first hit. So one of the uh, in recent history here, one of the things we experienced in the Irving area, Dallas area, and surrounding communities was some earthquakes, and we could definitely feel the P waves from those. They were centered over the old Cowboys Stadium in Irving, and so we were all pretty close to them if you live around here. So a lot of us felt some shaking from that, and that was our P waves because we were so close to the epicenter of those earthquakes. And so just a quick, here's some different kinds of faults that you might have that could cause an earthquake. And all you have to do is have the big chunks of land or crust that you're seeing here snap in any of the given directions shown, and that can release the energy that we know of as earthquake waves. So after the P waves come by, you're going to have a little bit of a delay, and then suddenly you'll get what we call the S waves, and they're secondary or S-shaped waves. So again, you look at the P waves, P being primary or pulse waves. These are S waves, which are second to arrive or secondary, and they're actually shaped a little like an S if you look at that picture down below. So kind of easy ways to remember them. In physics, we call this a transverse kind of wave, just due to the fact of the shape and the way the movement of the wave is versus the actual vibrations that are occurring, which I'll show you in just a minute. So these are more like what you would think of as a traditional wave. They look like literally waves on the water that you would see at the ocean. So the key point, though, is that the ground is actually vibrating up and down while the wave energy moves out or left and right, which is perpendicular to that vibration. So I'll show you that in a little animation in just a minute. Definitely slower than the P waves, though. So that is what causes the delay. You'll get your P waves. Once an earthquake happens around the area of the earthquake, you'll feel P waves, and then there'll be a small delay, and then you'll get the S waves. And there's some other stuff in here about how they can't travel through liquids. That's important because parts of the earth are made of liquid, as you know. So the outer core in particular is the big one that can actually absorb these waves, and you won't actually let them pass through it. After P and S waves, you'll get another series of surface vibrations or oscillations called love waves, and they're long waves. They are sweeping, long, back and forth motions, and literally side to side. So you can see in this picture the kind of motion that you're going to experience. And you can kind of think about the progression here. Once you get P waves, you're kind of vibrating everything, and then the S waves kind of undulate and push things up and down. And so things are, you know, whether it's a building or a roadway or whatever, things are weakening substantially during these shaking events, and that can cause a lot of damage. And then these love waves come along, and they can really just kind of finish the job on you and cause a lot of collapsing and cracking and things like that. But they're very slow, so they'll be the last ones you receive during an earthquake event. So how do you actually capture all this, and how do we measure earthquakes? How do we know, you know, when one happens and where it is? Well, you got to use some equipment. And so we have this little device called a seismometer or a seismograph, which are slightly different. One is a more modern version, but either way, they sort of do the same thing. They are basically a weighted needle that is sitting still, and then if an earthquake happens, the earth will vibrate and the machine around it will vibrate and cause that little needle to actually draw with ink a series of waves. And so it's kind of like taking the shaking that an earthquake generates in the different types of waves that it makes, and actually draws them out for you on this barrel-shaped piece of paper. And if you look at the picture here, most of the time there's no action, so you just get straight lines. And then once it goes around one full time, it'll just move kind of down one line or a little space down. But then once the earthquake happens, in this one, you can definitely see where that starts. You can see your P waves arriving, and then there's a little kind of delay, and then you get your S waves, and so on and so forth. So pretty neat piece of equipment. If you want to see that in action, you can actually click the couple of links that I have down at the bottom of the screen. But I'm going to click one that takes us to a website, which is, it's the one that says waves there. I've got to unshare this screen and share a different one. So hold on one second. And what you'll see is it takes you here, which is showing us basically P and S waves. These are the most important ones for us as far as locating epicenters go. And it shows you what they do. So this is cool. There's a blue dot located just kind of in the ground somewhere, so you can see what actually happens as these waves pass by. And you can see they kind of pulse, like I said. So you're getting kind of a left to right push on that blue dot as that energy moves through. Those are your P waves. And notice that the dot will vibrate the same direction as the waves are moving, or back and forth within that same plane. So that's actually unique to P waves, because the vibration or the oscillation actually is in the same direction as the wave motion, which is kind of a left-right sort of thing. Whereas if we slide over here just a little bit, your S waves are going to be more like what we said. They're shaped like S's, and the ground actually vibrates up and down. So you get this kind of classic, like if you were floating out on the ocean waves or on a surfboard or whatever, those waves kind of move through and you move up and down like the blue dot is there. But the wave actually just keeps going from left to right. So that's what they mean by it's perpendicular to wave motion. The actual particles or the ground itself is moving up and down, whereas the wave is actually going towards the right, like you see here. So that is perpendicular. So that's how the waves work. And, if we were actually in a real class, I'd show you all that with a Slinky, which is pretty cool, but we don't have all that available. So that animation should kind of clear that up. So I'm going to switch us back to our slideshow really quick. And we are going to finish off talking about our waves. And basically what happens here is that once the earthquake is done and over with, we can take this barrel-shaped thing, peel that paper off, stretch it out, and you get something that looks like this. And what you have to do, though, is you have to throw down the time scale that you see along the bottom there. You have to actually put the, whatever times the clock was saying during all this, you kind of roll that out there and indicate whatever time, say, when the P waves got there. So if you look at this one, it looks kind of where the red arrow is pointing there. If you trace that all the way down, it's right around it's 0 hours, 4 minutes, and probably it's close to almost 5 minutes. So 0 hours and 5 minutes. Then there's a little delay there, obviously, in the S waves. come in later because they're slower. So you come down and you read that, and that's about 7 minutes, 0 hours, 7 minutes, 0 seconds. So that's how you do it. We're going to use this example in one of the next videos here because we'll kind of go through and use this seismogram as an example of how to locate how far away the epicenter distance was. This I'm just going to kind of really glaze over really quickly, just showing you that the outer core absorbs S waves, so they don't ever pass through this liquid layer of the core. And due to just other physics and refraction and reflection going on, there are areas of the Earth that don't feel earthquakes that happen at all, depending on where the earthquake is and where you're looking. But most places can feel something. So it's kind of a neat phenomenon that we could actually register an earthquake somewhere in this country that maybe happened over in Japan. So what we'll do is we're going to use our seismogram, that wave printout that happens from the actual machine, and we're going to make that our primary source of data so that we can figure out when, first of all, the earthquake waves arrive. Then we can use that to figure out how far away from the epicenter you are. And so that brings us to this chart, which is hugely important and kind of allows us to do it all. I mean, so without this chart, we wouldn't be able to go much further than that. So this allows us to figure out how far away from the epicenter we are. So there's a separate video for that. I'm going to kind of walk you through how to read this chart in general. And then this link that you see here on the left is actually a video tutorial for a more detailed example. So you can see somebody actually using it, and it's somebody else talking. So that'll probably be really refreshing for you. So I will see you in the next video. We'll talk about how to use this chart, and then I'm going to recommend you watch that video tutorial.